Today we are going to finish 10.2 Euler's method. So Euler's method is a numerical approximation to the solution of a differential equation. So Euler's method is numerical. We are trying to approximate the y value to any differential equation. For example, y prime equals e to the x plus something like this. So let's have a look at how do we do the Euler's method. So for Euler's method, we are trying to use several little tangent lines to approximate. We are going to follow the tangent lines to approximate y value. Let's have a look at the picture on the left. So given any initial point, we find the slope at the point. We follow the slope. We go delta x. That's our step size. We reach a1, and at a1 we find the slope. We follow the equation of the tangent line. We get to a2, and then we find the slope again. We get to a3 until we get the same. We get to the point we need. Okay, the conditions given the differential equation and the initial point where you start, and also delta x. We call it the step size. The Euler's method is the same thing as tangent line approximation, but we need a couple of different tangent line approximation here. The formula is given here, so to make it easier to understand, we use yx2 is approximately yx1 plus the derivative at x1 times delta x. This is the same thing as the tangent line approximation. Given x1, y1, and we use the slope at x1, we approximate what is the y value at x equals x2. The difference between Euler's method and Riemann sum is Euler's method, as we just went over, this is trying to approximate the y value given any differential equation to differential equation. However, the Riemann sum is trying to approximate an integral a to b fx dx. We try to use left, right, midpoint, and the trapezoid Riemann sum to approximate the area or the integral under the curve. Let's have a look at example here. Given differential equation and given our initial point and the delta x, which is our step size. So every step we go 0.5. Let's have a look at how do we find f1 using Euler's method. So from 0 with step size 0.5, we have two steps from 0 to 1, 0 to 0.5. Given 0, y value equals 1, f 0.5 will be approximately equal to f0 plus derivative at 0 times delta x. So f0 equals 1, we already given, and we need to calculate f derivative. Given y prime equals 2xy, so f prime at 0 will be 2 times x equals 0, y equals 1. From here, we get f prime equals 0. 0 times 0.5, this is 1. So f 0.5, y value is 1. So from here, we are going to evaluate f1, which is f 0.5 approximation derivative times delta x, which is f 0.5 give us 1, f derivative at 0.5 equals 2. We are going to use this differential equation again. X now is 0.5 and y value is 1. Give us 1. 1 times 0.5 is 1.5. This is our final answer for part A. Let's look at part B. So from 0 to -1. So the step is 0.5. So first we need to get -0.5. In this case, delta x is negative now, negative 0.5. So given 0, 1, f negative 0.5 equals f0 plus the derivative at 0 times delta x. f0 is 1, derivative, which is 0, give us, and delta x is negative 0.5, give us 1. And next, f negative 1 will be the f negative 0.5 plus the derivative at negative 0.5 times delta x. So f negative 5 is 1. The derivative equals 2 times x, which is negative 0.5, y, which is 1, give us negative 1. It's negative 1 times negative 0.5 equals 1.5. So this is our approximation. Of course, this is our approximation. You can also solve this by hand. You'll get a real solution for y. So this is your approximation using different steps. So that's your approximation. This is your real value. The difference between your approximation and the real value is the error. You're going to see some problems in the homework. How do we make the approximation better? So to make the error smaller, we need to decrease the step size. So every time we go a smaller step, this will make your approximation much more accurate. Okay, the homework is posted online. Any questions, let me know.